remembering exactly why we have this thermal factor, so let me ignore that. And then a closed interval. There's two loop momenta, and these three energies. I'm going to define this in a second. For those of you for which this is behind the plan, all I'm writing here is an energy conserving delta function. And what this is here is this integral over these momenta, where this is the k, and k. Here we have particle 1, 2, and 3. Yeah, so 1, I'm referring to this particle. Oh, I'm sorry. Let me say, this one is N2. This one is 1 plus N3. This is N1. So what we have here is just representing the following factors. We're integrating over all possible quanta that our target quantum can collide with in a way that conserves energy and momentum. And we have factors of N1 here, that's reflecting the number of these quanta that are present in the thermal state. Then we have these factors 1 plus N2, 1 plus N3. Those are the Bose factors for the final state associated with particles 2 and 3. So the decay is determined by the integral over all possible things that our particle can collide with, and a sum over the final states of things that the collision can result in. So this is just basically saying, in equations, what this picture is saying, that we can lose the quantum in our initial state by colliding with a thermal quantum. So the result of this calculation will be that the 2-point function decays at a very slow rate. If the coupling is small, this calculation is valid, but it decays in a way that's exponential. Roughly speaking, this is because the collision can happen at any time. So we get an exponential decay of roughly the probability that the particle that we inserted to begin with is still present in the state. So, okay, doing calculations, doing perturbative finite temperature calculations is possible, but it's annoying. And going beyond perturbation theory and studying this problem where we don't have a weak coupling is really impossible. People don't have a lot of techniques for doing this. But it's widely believed that this type of exponential decay of correlation functions is a rather universal feature of thermalizing quantum systems. There's another piece of evidence for this, which doesn't come from perturbation theory, which comes from numerical simulations of spin systems. So, for example, once we consider things, simple spin systems, like this one, like an Ising spin system. Where these matrices here are the Pauli X, Y, and Z operators acting at the different sites of the system. So this is an example of a nice chaotic spin chain, and enterprising people can take this type of thing and put it on a computer and exactly diagonalize this Hamiltonian into a matrix, and then construct the thermal state by taking an exponential of minus theta times the Hamiltonian, and then inserting these operators, one at time t and one at 0, and computing the answer, applying to the function of time. And what you get in this type of system is something that looks like exponential growth or exponential decay for quite a while. You can't go through very long times because the numerical problem, you can't study this in very large systems, because if we want to study n spins, then we have to use a Hilbert space that is a dimension 2 to the n. And the matrices that we'll be looking at, like Hamiltonian or the thermal density matrix, are 2 to the n by 2 to the n matrices. And your computer will just run out of memory. So people can study, it's a state-of-the-art that maybe 18 spins or something like that. So it's a very small system, but it's enough to see some of this very interesting dynamics. So these are things that one can do. One can study perturbation theory, and you get a slow but exponential decay, and you can study small systems, small spin systems exactly, and there you get exponential decay for a while. And this type of information has led to the following kind of picture for what happens to the 2-point function. It should decay exponentially for a long time. I don't know what I'm drawing here. It's something exponential. And then at very late times, if the system has finite entropy, it should stop decaying and start oscillating. The reason it starts oscillating is because in a finite entropy system, the 2-point function is a sum of oscillating exponentials. And that type of a function, a finite sum, or let's say absolutely convergent sum of oscillating exponentials, can't really go to 0 at big time. At big time, it can be small, but it has to be oscillating. The value that people throw around for this sort of oscillating floor is a value which is about e to the minus x. So there are wiggles on the scale of e to the minus x. And so the transition here happens at a time of about 10. If we assume that the 2-point function is decaying exponentially for a time of order of entropy, it will get down to a size of e to the minus x. And after that point, we imagine that it oscillates above this floor value. Okay. Yeah, I wanted to present an argument for the e to the minus x, but maybe I'll do that at another time. I got a lot of time to get over this. Yeah, so this is GMT, which is pure state is actually larger. It's e to the minus x over 2 for this final fluctuating floor value. Sorry? This is absolute value. Well, let's say the real part. We can drop the absolute value, but then hit better not the negative. Okay, so this has been a brief introduction to 2-point functions. The thing I want you to remember is that we expect them to decay, we expect them to decay exponentially. We can analyze it in perturbation theory and we get a very slow decay, but we can't analyze very well, even to calculate it conservatively as a whole. Okay, the other aspect of civilization that I'm going to discuss a little bit is this idea of a quench. So these 2-point functions are diagnosing what happens if we take an equilibrium system and perturb it a little bit. And the quench is asking a very different question. It's asking what happens if we take some state and excite it all of a sudden to some very high energy, very non-equilibrium state. So a model for this is a state Q, which is given by a product over X of some operators acting as X on the deck. So if we have, let's say, a lattice version of the system, then we can act at every site in the system with some local operator OX. Because we're acting everywhere in the system, we're going to raise the energy by an amount that's extensive. So we're going to turn this low energy vacuum state into some high energy thermal state. But it's going to be a very special kind of high energy state, where all the quanta are sort of uncorrelated with each other. You just created them all out of nothing, independently at each site in the system. And then what happens under time evolution is they interact and collide, and the correlations become more non-local. There are a few different types of quantities that one can imagine computing to diagnose the approach to equilibrium of this state Q. The next one is to consider the entropy of a subsystem A as a function of time. Okay. So at t equals 0, we just acted with these local operators. Actually, let's imagine local unitary operators on the vacuum state. So at t equals 0, the subsystem entropy will be the same as what we have in the vacuum. So at t equals 0, it'll be the same as what we have in the vacuum. But who can give me an idea of what type of entropy we should expect to have for a subsystem in the vacuum state? So suppose we have some region, is there some geometrical feature of the region that would tell us what to expect for entropy in the vacuum state? Sorry? Yeah, the area. So we expect to have the entropy of the subsystem A at time 0 to be proportional to area of A. And this will be divided by some UV cutoff. Okay, and at a very late time, we expect that this thing will approach an equilibrium thermal state, and there what does one expect for the entropy? Yeah, you're expecting excessive entropy, something proportional to the volume. Okay, and now instead of being a UV scale, this would be divided by power to the beta, the thermal scale. So in between, there's an interesting thing that will happen where the entropy grows from something proportional to the area to something proportional to the volume. And this is something that really cannot be computed. It actually hasn't even been computed how this happens in perturbation theory. The one case where it has been analyzed purely in field theory is the case of a single interval in a 1+1 dimensional field theory, where Calabrese and Cardi showed that this is completely determined by conformal invariance. And what happens is the entropy increases linearly from the area answer to the volume answer, and then it saturates. In general, though, this is much harder to calculate than these 2-point functions, but the time dependence of this function for t less than 0, less than infinity, is an interesting probe of civilization. How rapidly these correlations become non-local. Yeah. Could you say that again? How do you know that this function makes any sense? I mean, obviously, yeah, so no, the entropy makes sense for any system, for any state. It's just minus the trace of the density matrix times the log of the density matrix. So SA of t means the following. We compute rho A of t, that's equal to the trace over A complement of the state we have, which would be e to the minus I h t. Q into IHT. Okay. So this gives us the density matrix on subsystem A. And then we compute SA as a function of time, which is minus trace rho A log rho A. Yeah, so by entropy here, I mean the von Neumann entropy, which is defined for any state. Okay. Yeah, well, one expects it to be monotonic. Actually, one expects also that at early times they should grow linearly. Although I'm not sure that one expected that before they had been calculated using black holes. So, sorry? Yeah, so the type of function one expects for this is, one expects this. I better not draw the same thing. One expects something like this. That's the volume answer. Here I'm plotting f of t minus s of 0. So this is the type of curve one expects, and properties of this thing, like for example the initial slope, that will be interesting diagnostics of the thermalization property of the system. Yeah, in principle, one would like to be able to calculate the slope, let's say, to any order in the coupling in a weakly coupled field theory, but I don't think anybody knows how to do that. It looks like a very difficult problem. Okay, so that's the introduction to sublimation without black holes. We discussed the two-point function, where we can use perturbation theory, or we can use exact diagonalization. We also discussed this other type of probe, the quench, where you shock the system out of some low-energy state to some locally correlated to high-energy state, and then watch it equilibrate. Actually, I should have mentioned that for this system, you can also do these numerics on spin systems. Again, for systems of opposite size, like 14 spins, one can plot this type of curve that looks a lot like that. Okay, yeah. So yeah, this is another thing that you can do to take all of a sudden a high energy state that's very, very far out of equilibrium. In that case, you might not have this feature that the entropy is small to begin with, so it depends on what the Hamiltonian was that you were using to begin with. Okay. So now, let me give a quick introduction to chaos. So first of all, we've been discussing so far relaxation to equilibrium. In the decay of two-point function, saturation of these entropies, but in real-time dynamics, there are also features that are growing with time, exponentially growing with time. This is something that studying classical chaos is taught. So in 30 seconds, what I know about classical chaos can be summarized by thinking about this classic problem. The particle moving in a stadium that looks like this. This is a classical chaotic system. And what that means is that if we take a particle, let's say it's here, and it's going that way, that's on its trajectory, what has some kind of a path, if we could displace the particle a little bit first, and then set it moving, it would have had a very different trajectory. And for this type of system, the displacement delta x of the particle's trajectory before and after we perturb it, as a function of time, will be growing exponentially in time. Where the rate of exponential growth is called the Lyapunov exponent. So this is classical chaos. We would like to have some understanding of this in quantum mechanics. Actually, it's worse than that. This only happens for a much shorter time. This only happens until, let's say, delta x gets as big as it can. So in the stadium, delta x can only get as big as the stadium. That will happen in a time which is like, the log of the initial size of the perturbation, which is a much shorter time than any of these Poincare times. Okay. Yeah, so there was a nice paper written about this in 1969 by Larkin and Ovchinnikov, who pointed out that you can see a version of this classical chaos in a semi-classical quantum version of the region. So what they did was they considered the commutator of a momentum operator T with the momentum operator for this particle at time 0. So T of T with T at time 0. So they argued that in a semi-classical limit, this should be equal to IH bar times the Poisson bracket of T of T, P0. Okay? And the Poisson bracket. Probably I'll have the sign backwards. But so let's work out what that is. In this case, actually only one of these terms contribute. It's the term where, it's the second term here, where the derivative with respect to the momentum is hitting this vector. That's because the derivative with respect to position of this guy is 0. So what we get is minus I h bar times the derivative of T of T with respect to Q of 0. This is asking the following question. Suppose I take a trajectory, and I look at the momentum at some time T in the future, given the initial conditions. Now I change the initial position of the particle a little bit, and I ask what the new momentum will be at time T. And we've argued that these perturbations in these chaotic systems grow exponentially with a time scale set on the Lyapunov exponent. So we expect this to be proportional to IH bar times something which is exponentially growing. E to the lambda L times T. An important feature of this is that the sign in front of here can be both positive and negative. Momentum can be more in this direction or more in that direction, depending on exactly what initial position we're talking about. So if we average this quantity over the thermal ensemble as it stands, we're going to get something which is 0, or at least very small. So instead what we can do is we can consider the square of this quantity, and then average it. And then the sign that appears here will always square something that's actually still square something that's negative because of the vector I. So we can consider this quantity, T of T, T of 0 squared. And now we can average this over the thermal ensemble. Our expectation based on this argument is that in a semi-classical system, this should be proportional to minus is first where it's easy to land at L. Where length L is the Lyapunov exponent of the classical system. Oh, sorry, which you meant to. Yes, absolutely. The interpretation of this is somehow that, T and T of 0, they almost commute because we're in a semi-classical limit of this one system, but they don't quite commute, and that it's actually something that grows exponentially as a function of time. Okay, so we can generalize this outside this single particle stadium picture to a general quantum system, and we can consider the commutator between arbitrary operators, W of C. And it's nice to put a minus sign here, you can't put a minus sign, let's use that. Our expectation for this quantity, based on this analogy, is that it should grow, that these operators should fail to commute if the time separation is large, regardless of which operator T and W we started with. The fact that it's independent which operators we have is a version of the butterfly effect, which is that, we can think about this as giving us some kind of handle on how much measurement of W at time T can be screwed up by acting with V at time 0. And the intuition of the butterfly effect suggests that any experiment
So the purpose that I would try to follow is, first I would just understand the basic mechanisms
realize interesting properties of the standard model, particularly non-aggregate interactions and the shifts of chiral values. So the fact that the standard model is a chiral theory, that is that left and right values of kernels don't happen with interactions in the same way, is extremely important in model building. And in a sense, it is the only reason why we are right, and not all this is just a country, basically. So once we understand this basic mechanism,